All right, we're back recording. All right, let's take a look at these free response questions. All right, so first one, let's see if I can crop this up a little better here. There you go. I think it's better. Okay.
Yeah.
All right, so we got this mass C, which is on little wheels right here, and we're gonna drop 1/5 of math C on top. Right now, it says version J. I don't know what the difference in the versions are, but I was asking if you guys before class, and you guys were saying these look familiar. So, was it an entirely different question, or did they change this 1/5 to 1/4? I don't know. Okay, so at time 0, the cart's moving to the right with constant speed VC, right? And student releases the block from rest. Right, then at time t1, the block collides and sticks to the top of the cart. The block does not slide on the cart. Tell you what, when I first read that, I thought, that's a weird detail. I've never seen them like explicitly mention that. Although that comes around later on, like later they'll run back to that. Right? Guys, which means that is there friction between the block and the cart? There has to be, because if there wasn't, when the cart just keep on going, the block would just like slip off and just fall straight down. If there was zero friction. Okay? And what kind of friction are we talking about? Static or kinetic? Static, right? Okay, so just a little extra details. I'm just going to file that away in the back of my mind. And then at time t2, the block part system continues to move to the right with speed vf. Guys, with speed here, guys, everybody look here. Okay. Is speed vf faster than, slower than, or the same as the initial speed? Yeah, it's got to be slower overall, right? Because this is going to be what framework of physics? Conservation momentum, right? And the overall mass is increased. Right? And we're talking about momentum in the x direction, in the horizontal direction. Now you drop this block, that's something in the vertical direction. There's normal force from the floor, fold it up, but all that ends up just not mattering to the horizontal motion, right? Which is perpendicular to that. Right. So on the axis below, sketch a figure, magnitude of the x component of the momentum, so momentum in the x direction, okay, as a function of time. They say until t is greater than t2. So they want you to go past this dashed line. Okay? So what I'm thinking is, guys, at time 0, there was some initial momentum, right? Some initial momentum right here.
Yeah.
Okay, in the x direction. Now, what about when this block is landed and stuck to the cart? Is it the same momentum in the x direction? Yeah. What about when they're still moving on? Is it still the same momentum? That's what conservation momentum is. So what does that graph look like? Yeah, it's a flat line. It's just flat line straight across. Right? And now I don't have the scoring rubric, so I don't know exactly how this is scored. Right? But one of the details I would do is make sure that this line extends past T2, because that's exactly what they say there. Right? I mean, it just keeps going, right? Right. All right. Oh, by the way, here's all my solutions. I did double check. One of the there was a YouTube channel I linked to you guys to a few weeks back. A guy named Alan Sal, right? And I just linked him this morning also. Here, you know what? I'm going to show this to you guys. I pull up. All right. So I just posted this morning in Google Classroom in case you wanted to pull your laptop open and follow along. Here's a link to the FRQs that were again just released yesterday. And then I double checked. This guy got all the same solutions I got. Right now, some of these he solved a little bit different, or he thought about a little bit different, but we all got the same solution. So I triple checked my answers, and I'm quite sure on all these. All right. So part I. Derive an expression for the speed VF of the block cart system after time t2 in terms of mass of the cart, the initial velocity of the cart, that's what VC was, right? That initial velocity of the cart, and physical constants as appropriate. Right? That matters for anything. Begin your derivation by writing a fundamental physics principle or equation from the reference information. You guys, what fundamental principle are you talking about again? Yeah, conservation of momentum. Okay, so show you guys what I got line by line. Okay, so if I was doing this, well, I mean, obviously I would have written this. Right? That would be the first line I write. I'm guessing that was worth a point if you just wrote that. If you just wrote that, you probably got a point. Okay. Right. Now, the initial momentum of the system. What is momentum? What's what times what? S times velocity. So all came from the cart. So I did MCVC. Okay. And then after they stick together, isn't it M plus a fifth M, which would be like 6/5 M? Right. That's the combined mass. It's moving its own final velocity. Yes, it's all in the x direction. It's all in the x direction. Okay. Okay, so this comes out to, okay, it looks like that. Okay, now, regardless of what MC was, could be 1 kilogram, could be 5 kilograms. Does the MC cancel? Right. So that the final velocity should just be 5/6 of the initial velocity. Right. And the mass of the cart shouldn't show up in the final expression at all. Okay. Right. Do you guys get it? Because if the mass increases by a factor of 6/5, then the velocity should decrease by the same ratio, right? Right. The other way, so 5/6. Right. Up here. All right, what we got next here? Derive an expression for the change in kinetic energy. Change in kinetic energy. So, guys, should kinetic energy increase, decrease, or stay the same?
Decrease.
It's got to decrease. It's got to decrease overall, right? So I'm, just think ahead a little bit. I'm gonna make sure I have a negative in my answer. Although if I set up everything just naturally, there should be a negative at the end. And I don't know how they scored this, so whether you have a negative or not. If they dinged your point or not. Right, let's say, how do I do that? So guys, what's the formula for kinetic energy? 1/2 mv squared, right? 1/2 mv squared. So I'll say the initial kinetic energy of 1/2 mv squared in terms of with the subscript C and all that stuff, right? Okay. Now here, off this, I wrote this later because this is going to help me combine fractions later. Guys, could that be 6/12? Is that okay? Right. So here, I wrote that later, but we'll come back to that. Okay. Yeah. Now the final kinetic energy is also 1/2 mv squared, but it's a different mass and it's a different velocity. Different mass and different speed, maybe I could say, because we're talking about scalar. So, guys, this isn't a factor of 6/5 here, but a factor of 5/6 here, right? Which, in terms of momentum, ends up canceling out, but not energy, because on energy the speed gets squared. So, could this be like 25/36? Is that what that is? Oh, there it is. Got 25/36. All right. So I moved all the constants in front. I got the 1/2 there. I got the 6/5 here. This becomes 25/36, and I got MCDC squared. Is that okay? All right. Now, if I combine all these fractions to reduce that, I got 5/12 out of that, right? So, I forget what the math term is for that. Right? It's about factorization. Okay. So, all right. So here's what I got. My original kinetic energy, and this is actually where I write the side note here. So 1/2 is 6/12. Right? So now I got a common denominator, so I can compare this. So I start off with 6/12 of mv squared, and I end up with 5/12 of mv squared. So could the change in kinetic energy be final minus initial, just like that? Okay, what you end up with minus what you started, okay, which is going to be 5/12 minus 6/12 of the mv squared, okay, which is naturally comes out to negative 112 mv squared. Okay, so you guys did, show hands, how many of you guys think you got that? How many of you guys think you got that? All right, so you guys got that. Okay. Again, if you didn't get everything, if you at least wrote kinetic energy is 1/2 mv squared, I bet you got a point for that, and I don't know how many points this was altogether, but you may have picked up partial credit if you. Okay. Yeah, some of you guys got the whole thing. Yeah. I don't know. I know that 2 of them were worth 10 points. One of them was worth 8. One of them was worth 12. I think is the experimental design worth 12, I think. Okay. Huh? The experimental design was worth 12. Yeah, okay. So this was either 8 or 10. Yeah, 40 points total for the FRQs. And then you guys, of course, had 40 MCQ. That was separate from this. Right. Okay. All right. Consider the case where a new block is dropped and collides with the top of the cart. Here we go. Now we're rounding back to that sticky versus slide detail. The new block slides along the cart during the collision, but does not slide off the cart. Right. So I'm thinking maybe there's some initial kinetic friction, but eventually becomes static because it eventually sticks to the cart. It just slides a little bit. Right? The time interval, the new block collides with the cart and they move together is delta t. During delta t, there is a frictional force between the new block and the cart. Yeah, of course, there's a frictional force, if it eventually sticks to it, right? Kinetic followed by static friction. Indicate whether the x component of the momentum of the new block cart system increases, decreases, or stays the same during delta t. Right, guys, does conservation of momentum still apply? Is momentum still conserved? Which box? Here, let's see. Show hands. How many guys think it should increase? Who says increase? Who says decrease? Who says remain constant? Yeah, I would have checked that one too. It says remain constant. Right? Remain. Yeah. Okay. Yeah. Yep. That's what I checked. Just like you guys are all saying. I think everybody said that. Right. Now, guys, would this change the end result? Like if you count off a couple of seconds, time t2 and then keep scrolling, blah blah blah, right? It's gonna have the same final speed as before, like the 5.6 BC. Is that still the same? Yeah.
Can you also say that since it's between the two blocks and it's a the same system, there's no external work on it?
Exactly. Yeah, that's the explanation. Yes, you get the justification. Yeah. So I'm trying to lead you guys towards that. It says justify your response. Right. So here's what I said. Here, spelled out so that as if I was writing this. It said the friction force is internal to block system rather than external. Right. See, like, what's external? Well, maybe a normal force, although that's perpendicular to the motion, so that doesn't do anything. There's nothing pushing or pulling it horizontally, right? Sorry, scratch that. The friction force is horizontal, but it's internal to the system. It's just holding everything together. Okay? So because of Newton's third law of motion, the force pulling backward on one block, say like this card in the bottom, is exactly canceled out by an equal and opposite friction force on the other block, say this top block, which would pull it forward, right? These two friction forces, right, one's on the bottom block, one's on the top block, are both internal to the system and they exactly cancel each other out. Right? So there's no net effect. Oh, gosh. Did you have to what?
Do you think we had to mention third law?
Yeah, okay. Do you have to mention Newton's third law to get the point? Okay, I don't know. Yeah, because I don't have the scoring rubric. So, I would write that detail obviously because I wrote here to be safe. That may have been a box check to get a point. So, do you have to mention it? I don't know. Yeah. All right. All right, you guys hear that? Yeah. All right. So that was number one. Okay. All right. Number two. Block mass M released from position x equals 0 near the top of a ramp. The ramp makes the angle theta. Right, they threw a little theta down here with a horizontal. Block slides down the ramp. Negligible friction. Aha, which I was guessing was going to be the case, but now we confirm that. At 8D. Okay, so we're going from looks like 0 to, well, did you guys count 12 tick marks altogether? Right, and every tick mark's like a D. So at 8D. The block starts to make contact with the uncompressed spring, which has spring constant K. The spring is then compressed and the block momentarily comes to rest at 12D. Now, guys, here, can you guys think of an animation? If there's zero friction, could this be the block earth spring system? And would that be a closed system? Right. So if you let us go for 1,000 years, we go like boing, 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 and we just do that for like 1,000 years. Right. There's no loss. Right. Okay. So notice when it says momentarily comes to rest, that would be like the maximum compression, but not like an equilibrium. Right. All right. Okay. And if it did eventually come to equilibrium, it would not be as fast as much. Right? Maybe half as much, I would guess. Figure 1 shows the instance when the block is at so x equals 0, x equals 60, and 10D. But guys, notice at 10D, even at 10D, look, they left little swish marks on it. The block is still in motion, isn't it? Still got some what kind of energy? Kinetic energy. In fact, I should have asked you guys, but you guys would have said this is what framework of physics. This is definitely an energy framework, right? Right. I see a height change, right? Isn't the block's weight like pulling it down vertically? Right now, of course, it's on an angle, but that sounds like gravitational potential energy. Some energy at some point it's going to be in the spring. It sounds like elastic potential energy, 1/2 k squared. That's some MGH going. We've got some 1/2 k squared going. And then at these middle pictures, the block is in motion. That sounds like kinetic. That's 1/2 mv squared. Okay. So we're juggling these three different forms of mechanical energy. Okay. Which is exactly where they go with the question. We got this energy bar chart, and well, let's get past this a little bit. Okay, let's go straight to the chart. Now they gave one of them to you. They said at this 10D right here. The energy divvies like this. Now, guys, if you add up all the bars, what does it all add up to?
12.
Yeah, 12 units. Let's call it 12 units, right? It's like 12 E naught, 12 units, right? Since this is a closed system and there's no friction, do these bars also have to add up to 12?
Yeah.
Yeah, that would be conservation of energy, right? That's what they want you to see, right? They want you to see that in like bar chart form. You just have to add up to 12. Okay, so let's make sense of this. Here I see we got here. Right, this spring is smashed somewhere out. Right. Oh. How about this? Guys, at 10D, you know it can go all the way to 12D, right? Right, and there's 12 tick marks all together. Right? So wouldn't the height of the block be proportional to gravitational potential energy because MGH? And that's also proportional to how far it slides. Isn't that true? Because isn't the height change equal to how far it slides times sine theta? But sine theta, regardless of what theta is, we don't even know what theta is, but it doesn't matter because sine theta is just some constant value. So here, if the block slides twice as far along the ramp, does it also change its height by twice as much? And its gravitational potential energy by twice as much? And the fact that they're giving you 2 units of potential energy, gravitational potential energy, that's really, really helpful because that immediately tells you that at 60, this gravitational potential energy has to be at what value? It has to be at 6, right? But you know what else is also true at this middle picture is any energy in the spring at all at that point? No. So for US, you did what? Maybe make a little line down at the 0 mark. All right, so I got 0 here, I got 6 here, and the bars have to add up to what again? 12. So how much is on the kinetic? Another 6. So I think it goes 6, 6, 0 here, right? You guys think 6, 6, 0, right? And then go back to the very beginning. This first one. Is the block even in motion? No. So kinetic energy would be what? 0. And spring energy would be 0. And gravitational potential energy would be what? 12. And for 2 reasons. One is that all the bars have to add up to 12. So 12 plus 0 would be 12. But also, it's at 12 units up. Right. So for all these reasons. All right. So see what I did here. All right, here's what I got. All right. Got okay, so here's the one they gave you on the right. Right, ignore these marks. Right, whoops, those little straight marks there. Okay. But yeah, right. So 6, 6, and 0 there, and 0, 12, and 0 there. Right? Right, okay. All right. Pointing. Figure 5 shows the block at x0 when the block is released from rest, and the block at 12D when it momentarily comes to rest. Again, that would be the maximum compression. Starting with conservation of energy, derive an equation for the spring constant K. Express your answer in terms of the mass of the block, the angle of the ramp, whatever D is, some scalar factor of the distance, and physical constants. You guys, what physical constant do you think would be important? Gravity field. Do you think this would play out a little bit differently on the surface of Mars? Yeah, I think it probably wouldn't smash it as far on Mars, I'm thinking. But let's see, we'll come up with an expression. We'll see if that's actually true. Okay. All right, so over here. Okay. So very first step, I would write that right there. Show conservation of energy. Okay. I might do something like that just to fill in a detail, but unless I was short on time, I might jump straight to that step. Okay. So those all kind of go hand in hand. Right? Okay. So it starts off with all gravitational potential at the top. Okay. It's not in motion yet. The spring's not compressed, so it's all MGH. And where the spring is maximum compressed, all the energy would be in the spring at that moment. Right? And the block's not moving, so there's no kinetic, and it's also at its lowest height, so there's no more MGH. Okay. Okay. All right. And they want you to solve for K in terms of all this stuff. Okay. Now we're gonna have to do a substitution because here's mass of the block, that's fine. Here's gravity field, that could be a constant. But I think we'll have to do some substitutions. Guys, what could you substitute for H? Substitute for H. Yeah, isn't it yeah, this 12D is the length it moves, but times sine theta to get the height change. Okay, so I think in place of that H, I'm gonna do 12D sine theta. Oh yeah, that's it. Yeah, 12D sine theta. Okay. And what about this X? How much the spring was smashed? How much was the spring smashed from here to here? I think it was 4 units, right? It's 4 little tick marks. So I'll call that 4D. Wouldn't that be 4D? Right? So in place of the X, I'm gonna put 4D. And notice it's being squared. So does the factor of 4 also get squared? Yeah, sure does. Guys, what is 4 squared? 16 divided by 2 is 8. Okay, that's where that 8 comes from, right? So now it looks like that. Okay. Okay, and we just got to solve for this K. So guys, what's 12 divided by 8? That reduces to whatever what? Yeah, 3 over 2, I think. Is that right? 3 over 2? Okay. And then, I think one of the D's. Okay, divide down the D squared, and one of the D's can cancel. Right? That's, yeah. All right, there you go. 3 over 2, got the mg, got sine theta, all divided by d. Okay. So, well, you could think about functional dependence. You could say like if you had a more massive block, but it smashed the same, that would indicate you must have a stiffer spring and so on like that. Say gravity field. That's what I wanted to round back to. If you did this on Mars, if it did smash the same on Mars, that means that See, G would be smaller. That means you would have not as stiff a spring. So vice versa, if you had the same spring, it wouldn't smash as far. All right. Okay. Let's get there. Figure 6 shows graph of yeah, this gets fun. Right, so energy versus position. They want you to sketch and label a curve to represent the total mechanical energy of the block springer system as a function of distance. And notice they only went from 8D to 12D. You guys see they only went from 8D to 12D? Okay. And then also, let's do a double A, throw this in here too, to represent the gravitational potential energy, U sub G. All right, so yeah, I'll show you guys what I got. You guys tell me one first. Guys, what did you do for total mechanical energy? Straight line at 12E, is that right? Okay. Okay, so at 12E, label that the total mechanical energy right there. Right? Okay. Now here's the one they gave you. I just did this on my own paper. Okay, so here's the one they gave you. Guys, the spring energy, would this be a parabola? Parabola? How many of you guys think it's parabola? Yeah, I think so too. Because 1/2 kx squared, and here's your x down here. Okay, let's go there. Okay. How about gravitational potential energy? What's the formula for potential energy? Yeah, MGH, gravitational MGH. Okay, and if I go back to that bar chart, that could be helpful. Go back to that bar chart. Okay, so I remember that gravitational potential energy was just proportional to its location, since the straight incline sine theta was constant. So I'm going to start at 4 units, and it's going to go down to 0. In fact, it has to follow a straight line. Okay, proportional to h is MGH. You guys hear that? Okay. Now that's all they asked you to do. They want you to get this E and this MGH. Let me see, show hands. Guys, how many of you guys got this E correct? How many of you guys got this E correct? Total energy. All right, see a bunch of hands. That's awesome. How many of you guys think you got the gravitational potential energy correct? There you got that. Okay, yeah, looks like over half the class. That's awesome. Okay. Now here I went an extra step because this is going to lead to kind of the next question. Isn't there also kinetic energy, which they didn't ask you to draw? It's a little tricky. Oh yeah, go ahead.
Is it potential energy? Does that have to be a straight line?
Yes, it has to be a straight line because guys, gravitational potential energy, isn't that MGH? So gravitational potential energy is proportional to H, which is equal to some version of D sine theta.
Yeah.
Could be a height change. Yeah, so this one has to be a straight line. Okay. That's why you guys should have a ruler in there. Right, so I know everybody had a ruler. And then, guys, isn't it true that the 3 curves, the UG, US, and the K, have to add up to 12 units altogether? Okay. So I did my best last time to put this together to figure out. Well, I think the kinetic energy will look kind of like this, right? So it's a little tricky curve because at any point you can put your ruler at any point, and all three of these down here should add up to 12 units. Okay. All right. Okay. Because one of the questions coming up, might be the next question, is they want you to compare the speed at 8D and at 90. You guys see that? 8D and 90? And it's really close because if you think through energy, it's really a kinetic energy question, isn't it? Right? And it's really close. Right? But we're about to make sense of that. Okay. So, yep, that is the next question. Indicate whether the speed at 90 is greater than, equal to, or less than speed at 8D. Okay. Okay, hold on. You guys think about that. Okay. You guys think about that. Now, guys, get a real good look at, here. Get a real good look at that graph right there. And try to remember which box you checked. Okay. Everybody think real hard which box you checked. Right. All right. And then I got to pull up my notes. All right. Boom, boom. Right. So show hands. How many guys, sorry. Let me go over these. I don't know if you guys can read these. First one says at 90, it's faster than at 8D. The second box says at 90, it's slower than at 8D. And the third box says they would be the same. Okay. So show hands. How many guys checked the first box? Who checked the first box? First box.
Yeah.
Okay. Yeah, it starts to hit the spring at 8. Hold on. Where did it hit the spring? No. 12, 11, 10, 9. Oh, yeah, it was at 8D. Okay. Yeah, so at 80, it did start to hit the spring. So you can say, well, maybe some of its energy started to transfer into the spring, right? But don't forget too that it's still falling in elevation. Right? So there's like a trade-off, right? There's trade-off, right? Now, at a glance, my first thought was, they look pretty close to the same. But then, so, this is where they really want you to tease out the difference. Okay? You guys see here? If you look really, really, really close on this graph, right? Guys, at the 90 mark, is this parabola above or below or at the 1 look mark?
Right below.
It's a little bit below, right? And that's what makes all the difference. That's what they want you to figure out. Right? In fact, I can tell you exactly where it is. Because guys, let's come up with an equation for this. Oh, for this parabola. Can you guys say potential energy in a spring is 1/2 k x squared? Would that be true? Right. Here, let's solve for k, and then we'll come up with an exact equation. Because I know 0, 0 would work. If I plug in 0, I'll get 0. That's this point right here. And also, if I plug in, let's say 1, 2, 3, 4D, right, for 4D smash, I get 12 units of energy in the spring. So 12 units of energy. I'll just call it 12. Okay, this like I'm really cutting corners a little bit. Okay, that's if I plug in like 4 units and then square that. Guys, what's 4 squared? Divided by 2, 8. And what's 12 divided by 8? 3/2. Right. So it's like your K. Again, I'm leaving units off. I know that's really sloppy. I never do that. Right. But that gives you this equation. Spring energy is 1/2. It'd be 3/2, right? Newton per meter, whatever the unit is. Right. There's some unit here. Right. Times x squared. Right. That's like the equation. Right. Here, let's make sure this works. Because if you plug in 4 for x, what's 1/2 times 3/2 times 4 squared? Yep, that gives you 12. You guys see that? If you plug in 4 for x, you get 12. If you plug in 0, you get 0. That's 2 points on the parabola. Okay. Now watch this. What if you plug in 1 unit for x? And I'm getting that from here, just like 1 unit for x. You guys see 1 unit? Right? I should get something that's less than 1, right? Less than 1. That would match that graph. In fact, it's exactly 0.75. You guys see that? 0.75, right? Which is less than 1, which will tell you something. Okay. So here, trying to really walk you guys through this this thought process before I just show you guys the answer. Okay. So, at this 9D right here, okay, I know that this is at like 0.75. So if I go straight across, this is like at 0.75. Okay. But what about this gravitational potential energy? Didn't it drop down 1 unit all the way down to 3 E0 right here? All the way down. Okay. So while the block is starting to smash the spring, it's lost 1 unit of gravitational potential energy, and it's only picked up 3/4 of a unit of spring potential energy. So does that leave a little bit of excess to go into kinetic energy, which would be at speed? So where is it going faster? It's got to be at 9D. It's got to be at 9D, right? Which would be this first box right here. Would be 9D. Okay, got to be going faster. Right. All right, so okay, that's why I check right here. And did they say justify that? Yeah, justify how it's consistent with those energy curves, which is kind of what we've been doing. But here's how I wrote it, and I spelled it out. I said at 8D, the gravitational potential energy is 4 energy units, and spring is 0, and the sum of energy is 12. Therefore, kinetic energy would be 8 energy units, right? Okay, so at 8D, the kinetic energy is 8 units. Okay? But at 9D, now the gravitational potential energy is only 3, so we went from 4 down to 3. And the spring is from 0 up to 3/4. So, you guys remember that? I drew that for you guys? Right, which I didn't write down, but we just went over that a minute ago. Right? And the sum of the energy is still 12 units. So that makes the kinetic energy 8.25 energy units. And since there's more kinetic energy at 9D than 8D, then it has to be faster speed. Okay? Like that. Okay. You guys good there? Are we good? All right, 8 questions so far. You guys ready? All right. Next one. Ooh. Number 3. From that diagram, does that it look like the seesaw question? The seesaw? Okay. So do you guys think it's going to be a torque question? I mean, just from the diagram. Right. So if you treat this pivot point right here as the point that you sum the torque about, when the spring scale times 50 centimeters on the left balance out with the weight of the block, so mg, so don't forget the g too, right? So mg times whatever radial arm distance this is over here. something like that, right? The clockwise and the counterclockwise torque have to zero out relative to this middle position. Okay, and then whatever upward force is at that position causes no torque about that point. So that's why you want something torque about there. Okay. All right, but we haven't even read the question yet. So this is your experimental design. Yes, this would have been your 12-point question. Students have a spring scale of negligible amount, one end of a uniform meter stick. Right, so the fact that the meter stick is uniform means that its own torque cancels out, so you don't have to worry about considering the torque of the weight of the meter stick. Right, there's a hook of negligible mass fixed to the top. Of this mass. Okay, and anyway, you can put this block at different locations. So 60, 70, 80, or 90 centimeters. Students are asked to take measurements that will allow them to create a linear graph. Yep, there it is. Right. AP loves linearization. There it is. That was going to come up. Okay. Whose slope could be used to determine the mass and knot of the block. Describe an experimental procedure to collect the data, and then describe how that data could be graphed to determine M knot. Right. So here's my example. I said the students could hang the block at each of the positions 60, 70, 80, 90 centimeters. The students could read and record the spring scale reading when the block is hanging at each of these locations. Oh, the students should then repeat the process and obtain 3 recordings for each block position so as to reduce experimental uncertainty. Did they say that down here? Oh, there it is. Reduce experimental uncertainty. They always give you that hint, right? So you had to mention like take 3 readings or something silly, right? Right. Or maybe you had 3 different students look at it or whatever. Right. Different. Oh. So then how could you use it? Okay, well, I did a little math proof first, right? And then I continued it on the next page, right? So let's look at the math first for part B. How could you determine the mass? Okay. So I said the sum of torque goes to 0. That's the guiding principle. That was probably worth the point right there. And torque, you guys know, is R cross F. One version of it. Okay. So 50 centimeters times the spring force. So 50 centimeters times the spring force. That looks like counterclockwise. Has to balance out with the weight of the block. So that's M times G. Don't forget G. So M times G acting at X minus 50 centimeters. So whatever this X distance is, minus this 50 would give you this arm over here. Is that true? Right? Something like that. That would have to zero out. Right? And then you can do algebra. And remember, try and set up a linear graph. So some version of y equals mx plus b. So I got it in this form. So I got y value is the spring force. I got this mx. So here's your variable location. Guys, focus here. Guys, Cosby's trying to figure this out. Right? And then it did get this intercept, like this negative intercept here. I can show you exactly what that graph would look like too. Right? Oh, by the way, the link I posted, Alan Sal, he did a little bit differently. He went ahead and called this distance just d from the pivot point. And he solved it that way. So his looks a little bit different than mine. Right? If you want to see a little bit different interpretation, sometimes too. Okay. All right. So you take that equation. This is what that graph looks like. Right? And if you think about it logically, that makes sense too. Because guys, if you take this block and you put it right at the 50 centimeter mark somehow, if you hang it right here, then what does the spring scale read? 0. When the spring scale reads 0, because there would be no torque at all. You could take the spring scale off and it wouldn't even do anything. Right? And then as you move the block further this way to the right, doesn't the spring scale reading increase? Right? That's exactly what this says right here. Oh, I forgot to point this out. I did switch centimeters to meters just to be safe. That's usually a safe thing to do. I just wanted to. Right. So I did change this to meters, made this 0.5 meters. Okay. So I did that, and then I plotted all the points. It's like, yeah, that's exactly how that would look. Right. So the slope I described, because they asked you to use the slope. It works out to be, well, I got 20, and then 1/2 squared is the unit times the mass. Right. Guys, 20 is that really 2 times Earth gravity? That was another difference that Alan Sal did differently than I did. He wouldn't have had left G in there, so he just called this 2G. He called this 2GM would be the slope. Right? So you can find the slope and call that equal to 2GM. Can you guys do that? Or like I did, I just went ahead and plug in G is 10 meters per second squared. Right. So students should graph the spring scale reading on the vertical axis versus horizontal position on the horizontal axis. So spring Fs versus X. Okay. The slope of the graph equals either 20 times m. I also threw the unit in there, 1/2 squared. Or you could do 2GM. That could be perfectly fine too, 2GM. Right? Alternatively, you could actually use the y-intercept, because if you notice, really pay real close attention here. Go back. Right. You guys notice that the mass of the block, which we're trying to find, also shows up in the intercept. You see it, right? Which would, I'm talking about the y-intercept, which would be like way down here. Although they were trying to navigate you guys towards slope. So hopefully you pick the slope because they were talking about slope. But that would be another way to do it, right? And here's why that makes sense. I really want you guys to see this. I suppose there was a one more hole and it was right at the 100 centimeter mark. You got that 100 centimeters? And you hang this block right at the 100 centimeter mark. Okay. You guys see this thing would be symmetrically balanced? So suppose the block weighed 10 newtons. What was the spring scale read right here? It would be 10 newtons also, wouldn't it? Right. And I want you to see the symmetry from this graph. So if I extend this a little bit, wouldn't the 100 centimeter mark be like right over here? And so you could extend this up, one more tick mark, bing. And would this be 1, 2, 3? I have 4 tick marks here, but it would be 5 tick marks up. Is that true? Right. And would this be 5 tick marks down? It'd be the exact same force, wouldn't it? Just the other way. Yeah.
So is the spring scale upside down? So the bar was pulling on the thing.
Yeah, the spring scale is always going to be in tension, right? Because right, the block's trying to pull this way. The spring scale is always going to be in tension. Now, according to my graph, here's one nice thing about physics and math too is sometimes you can see some additional possibilities that maybe weren't immediately obvious, right? This negative part that I dashed, that's where the spring scale would go into compression, which it can't do. But if maybe you had a force probe and you go into compression somehow, you could get a bunch of points down here too, right? So if you replace the spring scale with a force probe and you start hanging the weight on the left side, then in that case, the spring scale would go into compression, wouldn't it? Or you could hang the spring scale this way. Okay, either way. Right. All right. Okay. So okay, if you hang the spring scale this way, that only works if the block is on the left side. No, it would still work. It would still follow the exact same equation because it's all part of this line. So it would still fit exactly in the same equation. Yeah, so it would still work. Yeah. Yeah, still part. Oh, and then you guys had a poster that looked like this too, right? And I think I gave you guys a textbook question that looked like this too. And yeah, so definitely cover this one too. Right. So they make this angle.
I did the read, I remember it.
Right. And they're changing the angles. So they got different angles here. They got different corresponding tension forces. Right. Now I was thinking like I do see all these other pegs they could attach it to. One thing I was wondering was like, are they changing the location or what are they changing here exactly? Now I derived this because they said students correctly derive, blah, 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 blah. And you guys knew this was coming up, right? Students correctly derive an expression you've never seen before in your life, right? Because they did that on every practice exam, right? Now I wanted to derive that myself just so I could be for sure that I knew exactly what I was looking at. So, now my picture's not exactly to scale, but it wouldn't be something kind of like this, like the weight of the bar is trying to pull down, the string tension is pulling up to the left, and there's another force here up to the right. But if you sum the torque about this point, you can just ignore that one and say, I got clockwise versus counterclockwise. And here's your guiding principle is that the torque zeroes out. Is that true? Right. So at 60 centimeters, and then here's where I figured out it was locked into 60 centimeters because you had to have 60 centimeters here to reach their correct derivation. Right? You have this tension force at sine theta pulling straight up. So wouldn't this be Ft sine theta, right? You have the perpendicular component. Right? And then if you subtract it at 50 centimeters out, would be acting the weight of the beam, right? It's a uniform beam. So you treat its weight as if it's at center mass. So that'd be mg, right? That has to zero out in terms of torque. Yeah, my picture is not quite to scale. This would be 50 centimeters. This is 60 centimeters. You guys get the idea there, right? Okay. So then if you do a little algebra, boing, you get exactly what they said was the case. Okay. All right, that all right? Okay, everybody go up to here? All right. All right. So no, you didn't even have to do that though. You could just take their word for it. Okay. Students create a graph with 1 over sine theta on the horizontal axis, which they locked in right here. It looks like it goes up to 3 units. By the way, this is unitless. Do you guys notice that? Because sine theta is just a ratio. So this is a unitless. You could also call that, what is that, cosecant? I think it's the same thing. All right. So, all right. Indicate what measured or calculated quantity could be plotted on the vertical axis to yield a linear graph. Oh, we're back to linearization again, whose slope can be used to calculate an experimental value for the mass of the meter stick. What do you put on the vertical axis? Now, there's lots of potential correct options. So I wrote 3 here. We got, wait, did I show you guys this yet? What is this? Oh, right. So I took their derivation, right, which we proved anyway. Okay? And I said, how can I rearrange this to look like y equals mx plus b somehow? Okay, so I know that 1 over sine theta has to be the x-axis, so I pulled this out to the side. I see that could be 1 over sine theta. So there's my x-axis right there. Okay. We want to somehow get the mass in the slope, which it looks like it kind of is right here. Now you could put on your vertical axis, you could just put the tension force. That'd be fine. You could do that. Right. I wanted to do something a little different. Yeah, guys, could this be your y-axis? This could be your x-axis, and then that right there could be the slope. Y equals mx. That could do it. Right. Now I wanted to go one more step myself. I said, I'm going to take this 5 over 6g. And I'm going to flip that to the other side so that the slope is exactly the mass. So that once I get the slope, I don't have to do any more math. It's already taken care of. Is that you didn't have to do it, but you could have. So here are acceptable vertical axis, x-axis answers. I mean, here's 3 of them. You guys probably had one of these if you did it right. There might be a couple other ones too. You could just go with the tension, right? That could do it. In that case, the slope would be 5/6 of the weight, right? Oh, wait, did they ask for mass or weight? Mass? Yeah, they did ask for mass. Okay, so you have to also consider g, right? You could have moved over one of the variables like g, right? But then the slope would still be 5/6 m, so there would still be some math you'd have to do, right? Or here's what I actually did. I actually did this bottom one. Right? So the slope would be exactly the mass, right? You could do any of those. Right? So I'm going to continue with this bottom version on my notes. Alan Sal on YouTube actually went with this top version right here. So if you want to look at his solution, he went a little different. Okay? But we both got about the same answer though, okay? By the end, because no matter how you do it, you get the same. Now they gave you a table with just 2 columns. Normally AP gives you extra columns that are blank. I don't know why they didn't on this case, but whatever, right? It's a little different. But I extended a table. So I put it all on this page right here. We got, okay, I did 2 and 3 all together here. So here's what they gave you. They gave you these first 2 columns. I said, well, 1 over sine theta. I went ahead and plugged that in my calculator. Hopefully your calculator was in degrees and not radians. Otherwise, it wouldn't have made no sense. Okay. All right, so make sure your calculator was in degrees. Okay, see all degrees. All right, and then I took what I wanted to put on the vertical axis. You guys remember I have this really weird manipulated vertical axis? Yeah, you could have just done the tension. That would have been fine. I went with this manipulated version. So the slope is exactly the mass, and I'm done. Right. Now, when you plot all the points, ideally what you're supposed to do is, see, they give you a grid. You're supposed to draw a line of best fit and pick 2 points on the line of best fit and do a rise over run between those 2 points. Now, since I did this on extra copy paper, I don't have that nice grid. So what I did was I said, well, it looks like my line of best fit, which I just whipped off as best I could, best fit, is parallel to these 2 dots. Then I did rise over run between those 2 dots, which by the way is these 2 points right here. Here, let's do this. I'll just on the calculator screen right in front of you guys. Let's do rise over run. Here, I'll mark this out and make it more obvious. So I picked these 2 points, which I said is parallel to our line. Did that rise over that run to get this slope, which is parallel to the line of best fit. Okay. So what is this rise right here? So looking at the difference between these 2, let's do 1.56 minus 0.96 in parentheses. Right, put that in parentheses. Okay. Then divide by, and my run is the difference between these 2 right here. 1.7 minus 1.02. So 1.70 minus 1.02. Like that. Is that true? All right. Okay. And okay, when I did that, I got this mass. Let's see if that's the same thing. Yeah, the same thing. I got 0.88 kilograms. Okay, guys, that. Okay. Now, when Alan Sal did this, he first did something really similar to what I did, a little different. He got 0.87, right? But then he did it a different way. He actually went to Excel. Do you guys know you can go to Excel or maybe use Desmos? He used something. He actually plugged in these coordinates, and he actually did the proper linear regression, or he had the computer do it. There's a very advanced statistical method to do it, and you just let the either Excel or Desmos or something do it. Right? And he got 0.99 kilograms. Okay, so right. So we got 3 values. We got 0.87, we got 0.88 right here, and the full value is like 0.99, right? Did you guys get somewhere around there about a little less than a kilogram? A little less than a kilogram? Okay, if you got a little less than a kilogram, then you probably got full credit. Yeah. All right. So nice. Was there anything else on that one? No. Okay, I think that's it. Yeah. Okay, you had to draw a line best fit and then calculate the experimental value. Okay, and that was all. We did all of that. Okay, all that. All right, so you guys get on number 3. All right, number 4. Hey, got the swimmer with the block. Right. Hey, let's go with the block, and yeah, it floats to the top. Well, actually, it should accelerate. You know what? Here, I think the only time the thing I have time to show you guys right now is the free body diagram. You guys come up with a free body diagram that looks approximately like that. They said also ignore drag forces. One of our review questions actually looked a lot like this, because realistically there would be some water drag. They said don't worry about the water drag, so we're going to ignore water drag. Okay. All right, so we'll hit a pause point right there. Tomorrow I'll go over the rest of number 4 with you guys. Okay, and then we'll do more stuff, fun stuff to finish out the week.